This lesson is on continuity. So the first thing I want to point out is continuity is just what you think it is. If something is continuous, you can trace it with your pencil and not have to pick up your pencil. Don't forget that as we get into more complicated definitions. Just think, okay, when can I not trace it, or when do I have to pick up my pencil? That is going to help you with just making it make sense. First of all, I want to point out the difference between discrete and continuous. Some people think they're opposites, and they are total opposites. Discrete is kind of like a scatter plot. It's separate points that are not connected. Continuous is smooth and traceable. But a lot of functions fall somewhere in the middle of those two. They're not totally discrete or not totally continuous, although there are many that fall into both of those categories. But we will work with some that aren't completely discrete or completely continuous, and we will talk about the differences. The main differences are types of discontinuity, and there are 4 types. The first is called point discontinuity or removable discontinuity. This is when there's a hole in the graph, and so the graph's going along, you have a hole, and then it goes along after that, and the hole is just at that one point. If you were tracing it, you would have to pick up your pencil to get to the other side. So again, instead of calling it a hole, now we are going to call it point discontinuity or removable discontinuity. The reason it's called removable discontinuity is because you could technically take whatever this function is and create a piecewise function and fill the hole with something using a piecewise function. Another type of discontinuity is a jump discontinuity, and it's just what it sounds like. Your graph jumps from one place to another, and so I've just sketched something out here. It still has to pass the vertical line test, so I could have one filled in dot and one open dot, but I couldn't have both filled in because it wouldn't pass the vertical line test. Now they could both be open, and it would still pass the vertical line test as long as it passed before and after that. But if the graph jumps, it's a jump discontinuity. Infinite discontinuity is when you have a vertical asymptote, and I've just drawn one where the sides go off to infinity, but anytime that you were tracing this, you would have to trace, pick up your pencil, and jump to the other side to trace the second part. That is infinite discontinuity when you have a vertical asymptote. The last kind is a really weird thought, and that's oscillating discontinuity. And the best example that could ever come up that I have found is y equals sine of 1 over x. Now, I'm sure that this occurs in other functions or it wouldn't have its own name, but this one comes up the most as the best example here. So if you want to graph that in your calculator and see what it looks like, it's really interesting. What oscillating discontinuity is when a graph is going along and then near something that you're trying to find, is it continuous at that point or not, it's oscillating, going back and forth so fast that it doesn't nail down on a single place. If you graph this y equals sine of 1 over x in your calculator and you keep zooming in and zooming in and zooming in on 0, it's just going to go back and forth faster. And so it's kind of hard to wrap your brain around, but that's oscillating discontinuity. Okay, I have a big gold star beside of this because this is the thing that most people get confused on and miss questions about. This graph is a graph of a function. This one's a line with a hole in it. When there's a hole, you have to remember that the limit does exist. Why does the limit exist? Because both sides are going to the same y value. Okay, both sides are coming to that same place. And remember, limit means you can get close to it or you can touch it. So this gets close to it on both sides. It doesn't actually touch it because the point's not there, but the limit does exist because of the definition of limit. It's not continuous because it is a point discontinuity. The hole's not filled in, it's not smooth, it's not traceable. You'd have to pick up your pencil to go over that hole. But this is the big thing. Limit does exist when there's a hole, but it's not continuous. Keep those two things separate. Okay, in our first algebraic example today, we are asked to find a, and that would be the variable in the problem, so that f of x is continuous. So they've given us a piecewise function, and they want us to figure out what number a could be that would make this continuous. Well, what you have to know is that if it's a piecewise function, and this one is some sort of line, and it's connecting to a parabola, because x squared makes a parabola, and you want them to connect at the same place and just make a smooth, kind of funky looking graph. In order to connect at the same place, they have to have the same y value. And that means that if I have that x value on both functions, it has to have the same output. So what you do to figure this out is you plug the x where they meet, okay, and so in this case it's 2, into both x's, and you set them equal to each other because they have to equal that same output. So I'm going to say 2, and my screen jumped. Okay, so I'm going to say 2 times 2 minus 5, and that's going to have to equal a times 2 squared. So over here I have 4 minus 5, so I get negative 1, and then 2 squared is 4, so I have a times 4 here. Divide both sides by 4, and a is negative 1/4. So this would be the value I would need in front of the x squared so that these two graphs fit smoothly together. All right, I have another one here. Find m so that g is continuous. It's the same deal. We've got a line and a parabola, and so I want them to meet at the same place. So I'm going to plug in the negative 3 because that's where these two graphs meet. So m times negative 3 is going to equal negative 3 squared minus 11. And so m times, I left something off. Okay, now I have it right. M times negative 3 plus 4 is going to equal the negative 3 squared minus 11. Sorry for that. Now I have negative 3m plus 4 is equal to 9 minus 11, which is obviously negative 2. And I just solved this equation. So I'm going to subtract 4 and get negative 6, and then divide by negative 3 and get a positive 2. And so there is the m that if I had it right here as my slope, this line would meet this parabola. Okay, the next set of problems we're going to classify the discontinuities. In other words, we're going to name whether it's a point discontinuity, a jump discontinuity, an infinite discontinuity, or an oscillating discontinuity. And so this first one is going to remind you of our lesson on rational functions and their graphs. And so the first thing that I notice is that I want to cancel out these x minus 1s. And if you'll remember, if you want to cancel them out, that means there's a hole in the graph. And so that hole is at a positive 1, because if you plugged in a 1, 1 minus 1 would be 0, and that would be what gives that piece 0. But instead of calling it a hole, now I'm going to call it a point discontinuity. So point discontinuity at x equals 1. The other discontinuity that I have has to do with this x minus 3, because if you remember, a 0 on the bottom that isn't already a hole is going to give you a vertical asymptote. So what would make this piece be 0? And that would be a positive 3, because 3 minus 3 would be 0. So we're going to have a vertical asymptote at positive 3. So in the continuity language, that would be called an infinite discontinuity. And that would be at x equals 3. Okay, the next one is a piecewise function, and we kind of have to think about it as toolbox functions and what we did on example 1 and 2. I have a parabola and a line, and a parabola is continuous, so I know that before 1 this graph is continuous. A line is continuous, so I know that after 1 this graph is continuous. The question is, do those two meet? Like in 1 and 2 we were finding the numbers so that the graphs would meet. Here the question is, do they? Because we don't have a variable to find to make sure that they do. So I have to do a little bit of work. I'm going to plug in 1, so 2 times 1 squared minus 1, and see what that output is, and that would be a positive 1. And then if I plug in 1 to the bottom part, because that's the place where they meet, 1 plus 3, that's going to give me 4. Now, the fact that they got different outputs means that this graph jumps. This parabola is going along, and then it hits the point 1, 1. This line picks up at the point 1, 4 and continues on. And so there's a jump between these two. So this is a jump discontinuity at x equals 1, because that's where they're supposed to meet but don't. All right, number 5 is another one. This one's a little bit more interesting, I guess. It has 3 pieces. Notice what's happening. You have x before 1, at 1, and after 1. So just like in example 4, we need to look at the before and after. Before 1, x squared plus 3, that's a parabola, and so that we know is smooth and continuous. After 1, it's x plus 3, that is a line. Lines are smooth and continuous with no problems. So before 1 and after 1, there are no problems. But we come up with the same question as we had on 4. Do they all meet at the same place? And in this case, all 3 of them are meeting at 1. So they all need to have the same output. And obviously that's a 2 because that middle one's 2. So let's plug in 1 and see what we get. The first one we have 1 squared plus 3. And so that would be 4. The second one, we know the output has to be 2. And the third one, we have 1 plus 3, which is also 4. So this is a situation where both sides are going to 4, but the point is at 2. And so this is what I was talking about with the yellow star. If both sides are coming up to 4, and the point is at 2, that's a point discontinuity. So point discontinuity, and that's at x equals 1. Both sides are there, the limit is there, the limit would be 4, but it's not continuous because the point is not filled in, it's not smooth, you'd have to pick up your pencil. Alright, and then the last one of these, example 6, is x squared where x is not 0 and 3 where x is 0. Well, if it's not 0, that means it's before and after 0. It looks like a parabola. So this is a parabola everywhere but 0. And since we know what plane x squared looks like, it's a parabola, except it has a hole right there at 0. 0, 0. Now, at 0, that y value is 3, so it's saying there's a point at 0, 3. So this is similar to situation 5, where it is a point discontinuity. The point happens to be somewhere else. So point discontinuity at x equals 0. Now, the examples I showed you were all discontinuous. That doesn't mean that everything that you come across is going to be discontinuous. If this had been a 0, then the point would be filled in, and that would be continuous. On number 5, if this had been a 4, then the point would be filled in, and that would be continuous. Example 4, if these two outcomes had been the same, it would have been continuous. So just because I've showed you all of the discontinuities doesn't mean that you won't come across things that are continuous. So you have to check them and you have to think them through. Okay, properties of continuity. F and G are continuous functions. We're going to assume that. Then we know other things. So think of like f as maybe x squared and g as an mx plus b line. Okay, if you do a number times a continuous function, then that function is also continuous. It's really just vertically stretching or shrinking it. So it's still continuous. It doesn't change that. If you add two functions that are continuous, well, if it's continuous, it has a domain that hits all these x's, and this one has a domain that hits all the x's. You can put them together and they still have that nice domain. Again, if you multiply two continuous functions, it will be continuous. This was supposed to be divide, so go in and make that f divided by g, if the two functions are divided, it's still continuous everywhere except if g is 0. So everywhere except where g of x equals 0, because you still can't have the denominator be 0, it's a fraction. Okay, so adding or subtracting, multiplying, dividing is okay unless you have a 0 on the bottom. And then f of g of x or g of f of x, that's a composition. So compositions would also be continuous. Okay, now we're getting into kind of AP ready stuff. You have to explain things. And so we're going to use those properties to explain 7 and 8. 7 says, explain why f of x equals sine x plus e of x is continuous. So we're going to write a nice sentence. Obviously, sine is a continuous function. It's that nice wave. And it's nice and smooth. E to the x is your exponential graph, and it's nice and smooth. Both of these are continuous. This is like the f and g that I was talking about above. They're continuous, and we're adding them together. So their sum is continuous. So my nice sentence is, since y equals sine x and y equals e to the x are continuous, so I'm saying they're both continuous, their sum is continuous. Notice a couple things. I used y equals with both of them because I need to treat them separately as functions. I say that they're both continuous. And then I said their sum because that's what we're doing in this equation. We're adding them, so their sum is continuous. So you may have to remember words like sum and difference and product and composition. All right, number 8. Explain why g of x equals absolute value of x squared minus 7x plus 3 is continuous. This one might be a little harder to see because you don't see the plus or times or something. This is the composition. The x squared minus 7x plus 3 is inside of an absolute value function. So that makes my sentence include those two things. And the absolute value function is that nice v function, so it's continuous. X squared minus 7x plus 3 is a polynomial x squared, making it have the u shape, so that's continuous. So my sentence will read, since y equals absolute value of x and y equals x squared minus 7x plus 3 are continuous, their composition is continuous. And again, composition is your f of g of x or g of f of x. One is inside of the other. Okay, again, make sure to include the y equals with both of those functions separately and the word about what's going on, in this case, composition. Okay, our last two examples are sketching, and I know we've sketched some things recently with infinite limits. Here we're going to sketch a graph that hopefully has all of these qualities. And everybody's can have a little bit different shape, but they have to meet these requirements. So 9 is sketch a possible graph where the limit as you approach 3 exists, f of 3 is 1, and f is not continuous at 3. So what they're saying is, when I get to x equals 3, my graph has to have a limit, so both sides have to go to the same place. It has to have the point 3, 1, but it cannot be continuous. That limit existing and the not continuous tells me I have to make a point discontinuity. The requirement that f of 3 equals 1 means I have to put a point at 3, 1, and I'm going to start with that so that I don't forget it. This is also something that needs to be a function, so I need to pass the vertical line test. So try not to draw anything that's going to not pass the vertical line test. Since this was my only numeric requirement, I can make my limit come down here or up here, wherever I want to do it to make a point discontinuity. So I'm just going to do it up there and be done with it. I can make the graph any shape I want to because I've met all the requirements. The limit as I approach 3 exists because both sides are going to the same place. F of 3 is 1, the point is there, but it's not continuous. It has a point discontinuity at 3. Okay, and our last example wants us to sketch a graph where f of negative 2 exists, so there is a point with an x value of negative 2. The limit as x approaches negative 2 exists, so both sides have to go to the same place. f is not continuous at -2. So this almost reminds us of that last one. If the limit exists and it's not continuous, then it has to be a point discontinuity. And then the limit as x approaches 1, so at a totally different place, does not exist. So let's start with that -2. They didn't give us a y value this time. They just said we got to have a point. So at -2, I'm just going to put a point. I'm going to put it on 0. I could have put it anywhere with an x value of -2. The limit as x approaches -2 exists, but it's not continuous. So I've got to have a point discontinuity there. I'm going to go down this time. Alright, so this part of the graph is meeting, well, it did before it disappeared, is meeting my requirements for the first part. Then the x approaches 1, 1's right here, it says does not exist. That means I can make it be any type of discontinuity that I want to because they didn't put any other requirements on it. So I could do a jump discontinuity, I could do an infinite discontinuity. If I wanted to, I could do an oscillating discontinuity. I think I'll do a jump this time. So I about went to 2. Let's see, I'll come up here and put a point here and then jump up and finish out my graph. The shape of the graph really doesn't matter as long as you're meeting these requirements and passing the vertical line test. And that concludes this lesson.